Hey there. In this video, I want to talk to you about uniform random variables. So these are a special kind of random variable that have really nice probabilities. In fact, the way they're defined is that every single probability is the same for a uniform random variable. And so let me first show you what a discrete uniform random variable looks like, and then what we're going to do is we're going to do an example with a continuous uniform random variable and compute some probabilities based on that. So, that's not skipping ahead. This is the example of a discrete uniform random variable. You roll a six-sided die, right? And you look at all the possible outcomes and their probabilities. Well, look, the outcomes are 1 through 6. Those are the values of my random variable. The probabilities are all the same. They're all 1/6. Every number is equally likely to occur on a fair die. And so the distribution function looks like this, right? Every single bar has the same height, exactly 1/6. That's what a discrete uniform random variable looks like. Well, what does a continuous uniform random variable look like? Well, it looks like this. It's just a straight horizontal line. It's just a horizontal line. That's all it is. So what this corresponds to is when you have a random variable, in this case x, and it can take on any value between, in this case, 5 and 20, and every single possibility is just as equally likely as any other possibility. So it's like every number between 5 and 20 is just as likely to occur as any other number. And that's what makes it uniform, and that's why this bar has just a constant height. Okay? So let's go ahead and compute these probabilities. If this is how x is distributed, what's the probability that x is less than or equal to 10? Well, what I'm doing here for less than or equal to 10, I'm finding it's this range of x's. And so I'm finding the area under the curve less than 10. And so I'm finding the area of this rectangle. Well, how do I find the area of a rectangle? Well, we talked about this in the last video. It's base times height, right? Oh, what's the base? Well, it goes from 5 to 10, so the base is 5. What's the height? Uh-oh, it's not written here. Does that mean we can't solve this problem? Well, no, it doesn't mean that. We can solve this because we know one important fact about continuous random variables. The total area under the distribution function is equal to 1, right? That's a property of probability distribution functions. The total area is 1. So maybe we can use that to find out what the height of this is. Okay, well, let's see. What's the width of this whole thing going from here to here? The width is 15, okay? So the total area, by the way, is base times height. That's the area of the rectangle. And we just said the base is 15. The height we don't know, but the area we do. We said the total area has to be 1. So look at this. We have an equation involving h. We can solve this for h, right? If I divide both sides by 15, I see that h must equal 1/15, right? These cancel over here. So h equals 1/15. So now I know the height. So even though they didn't give it to me, I can figure it out. Okay? So now I think we can go and do these problems. What's the probability that x is less than or equal to 10? Well, it's the area of this rectangle. It's base times height. The base is 5. The height is 1/15. So the probability is 5/15, or if you want to simplify that, 1/3. Okay? What about this one? The probability that x is greater than 17. Well, 17 is somewhere over here, right? And I'm greater than it, so I'm going to the right. So I'm finding the area of that rectangle, where we're starting at 17 there. Okay? Well, it's, again, base times height. That's the area. Basic geometry, right? What's the base? Well, how far do I have to go to get from 17 to 20? 3 units. Or if I want to do it a little bit more analytically, I would take 20 minus 17. 20 minus 17 is 3 times 1 out of 15. Well, that's 3 out of 15, which simplifies to 1/5. So the probability is 1/5. What about this next one? 8 is less than x is less than 13. Or another way to say it, x is between 8 and 13. Well, here we're going from 8 to 13, right? From 8 to 13. So I'm finding the area of that rectangle. Well, what's the width? Well, again, the analytical way to do it is 13 minus 8. 13 minus 8 is 5. That's the width. And the height is 1 out of 15. That's 5 out of 15, or simplified is 1/3. Finally, probability that x equals 7. Think about this one. If you don't know the answer to this, watch the previous video because I emphasized this pretty dang heavily in that video, right? What's the probability that x equals 7? Well, if it equals 7, we're just looking at this thin line here. A thin line is a rectangle with 0 width. Well, if the width is 0, the area is 0. Yep, for a continuous random variable, such a probability is always going to be equal to 0. Okay? Let me give you another example, all right, where we don't have a picture. Okay? Okay, so here's the example I've conjured up here. The doors of a train are 40 feet apart. Okay? You wait at a random spot on the railway platform. What is the probability that the nearest door ends up within 4 feet, more than 8 feet, exactly 7 feet away? These different possibilities. Okay? Well, what's going on here? The doors are 40 feet apart. So if I were to draw a picture of the train here, you know, they have a door here and a door here, and then there's another car, door here and a door here. So these doors are 40 feet, right? And these doors are 40 feet. And these doors are 40 feet. And it just keeps going like this, right? So you're just going to pick a random spot. And we have no idea where the train's going to end up. So this would be a uniformly distributed situation. The distance that we end up away from the door is going to be a uniformly distributed random variable. And it's a continuous one because it can be any number of feet, right? And it's uniform because it's not more likely for a door to end up any one distance over any other distance. It's completely random, right? So that makes it a uniformly distributed random variable. Now, what is the closest we could end up next to a door? Well, we could end up 0 feet away. This train, we could be very lucky, and it could be our lucky day, and the train could stop so the door is right in front of us, right? Joyous times. However, what's the furthest we could be away from a door? Now, you might, if you jump to the first thing that comes to your mind, you may have said 40 feet, but you got to think about that. I mean, you can't actually, if you're 40 feet away from this door, you're actually 0 feet away from this door, right? So you're actually 0 feet away from the nearest door. The farthest you can be away from any door is actually 20 feet. You could be unlucky and be standing right here, in which case you're 20 feet away from this door and 20 feet away from that door. So actually what we have here is we have a uniformly distributed random variable where the possible values go from 0 to 20. Okay, so remember the curve is just a straight line. The question is, what is the height of that line? Well, how did we do the last problem? We said that the total area has to be 1. Okay, so take a moment, pause the video, figure out the height of this curve so that the total area is equal to 1. Okay, so 3, 2, 1. Okay, well, you should have figured out that the area, as we said before, is base times height. The total area has to be equal to 1. The base is width 20. And so I have this equation. And that tells us that h has to be 1/20th. So that tells me the height here. Okay, so now I think we can answer these questions. right? What's the probability that the door stops within 4 feet of where we're standing? Well, within 4 feet means that it's 0 to 4, right? So we're finding the area of this rectangle. Well, the base is 4, the height is 1/20th, so the probability is, I'll just write P equals 4 times 1/20, base times height. If you simplify that fraction, 4/20 is the same thing as 1/5. Right? That's the probability. What about the probability that it's more than 8 feet away? Well, let's look at the picture. More than 8 feet means maybe 8's over here. More than 8 means it's 8 or more, right? So, well, more than 8, right? So it's over here. More 8 or more and more than 8 don't matter when it's a continuous random variable, remember. So it's the base times the height. What's the base here? What's the width? It's 12. So it's 12 times 1/20. Well, you simplify that. Let's see. That's the same thing as 6/10. That's the same thing as 3/5, right? 3/5. What's the probability that it's exactly 7 feet away? Right there at 7. Exactly 7 feet. Well, exactly 7 feet corresponds to an infinitely thin line. That's a rectangle with 0 width, so the probability is 0. So even when we're not given the picture to begin with, even if we're given a description, we can still solve these problems, right? We can, because it's such a simple distribution. It's just a box, right? We can figure out just by drawing a picture what the answer is going to be. Okay, so hope you found that useful, and that's uniform random variables. I'll catch you on the next video.